That means, as a summary, what we have shown so far, if we are given an elliptic function field, when the constant field is different from the characteristic of the constant field is different from 2, with the base point O or with the rational point O, we show the existence of two transcendentals that allows us to write the equation or the algebraic relation between x and y. And in the literature, it is, in general, this form is called the Weierstrass equation, or the Weierstrass normal form of f. Or sometimes we write this equation y squared is equal to f of x with degree 3 square-free polynomial. Where f of x degree 3 and square-free. However, as a statement, and conversely, we can also say that if we are given a function field f k of xy, where x and y satisfies this algebraic relation, indeed, it is also known that this gives us the elliptic function field. So that means it has genus 0 and there exists a rational place. However, to be able to see that, we need to consider the extensions of function fields, algebraic function fields in chapter 3. So to see that, in general, it's not easy. But at least we can say that we have the characterizations. I mean, whatever you see in the elliptic curve course, in the definition of the elliptic curves, will be essentially the same in terms of the elliptic function fields. And just briefly, again, this topic is also considered in chapter 3, but I just want to say we can also consider the canonical divisors. So that means they will be divisors of dimension 1 and degree 0. However, I mean, for instance, if you consider the elliptic function field k of xy or k of x, indeed the canonical divisors in the extension fields of any algebraic function field is determined by the, in some sense, related with the canonical divisors of the base field. And it's quite detailed, but just for the moment, I can say that the places of the base fields and the places in the extension fields are also related. In this case, if you are interested in chapter 3, you can see that if we write our degree 3 square-free polynomial as a product of some irreducible monic polynomials, so that means R can be at most 3. And if we denote the places which are generated by this irreducible polynomial in the base field, like P1, P2, it can be at most P3, or P1, P2, or only P1 if it is irreducible. And I will just present it as a fact. It is known that there exist also places which in some sense corresponds these places in the rational function field, whatever this correspondence means. And again, for the P infinity, the corresponding place will be the R base point O. So the canonical divisor, so it's not going to be so obvious, but in general, are taken as a sum of these places minus 3O. And of course, there are many details, but this is just something I wanted to say, but you are not responsible for that. And for two divisors in the elliptic function field, we know that it's also general. If they are equivalent, then they have the same degree. But we will now give a counterexample. We don't have the sufficient condition. And in order to see that, we will use, you can also check Silverman's The Arithmetic of Elliptic Curves book, which shows us if we have two equivalent rational places, they are supposed to be same. So in order to see that, we can suppose that we can consider two rational places which are equivalent to each other. And by the definition of the equivalence, we know the existence of a function x whose principal divisor can be written as p minus O by p minus q. In particular, we can also take q as the base point O. So you can also come across this notation. And since the degree of q, by the way, I think it's better to fix the notation. Our claim is that P and Q are equivalent if and only if they are equal to each other. Here, P and Q denotes two rational places. And if you consider the Riemann-Roch space of the divisor Q, we see that indeed this function lies in L of O, and by applying the Riemann's theorem, since it has degree 1, which is bigger than or equal to 2g minus 2, in this case, we're in the case genus 1, its dimension is going to be its degree plus 1 minus g is 1, so that means this is isomorphic to K. So this function, which gives us equivalent, should be constant, and this shows us indeed the constant principal divisors of the constant must be 0 because they have 0 valuations, and this shows us indeed two places must be the same. So indeed, by this, let me say it, observation, or with respect to this characterization, we can say that if we consider two distinct rational places, it means they cannot be equivalent, and P minus Q indeed is not principal. And in this case, indeed, it also gives us the counterexample, because if we consider two distinct rational places, which are different to each other. Yes, I have already mentioned it. Then, thanks to this observation, we can't get the equivalence even though they have the same degree. So this gives us counterexample. For the sufficient condition of this statement. And as a corollary of this observation, you can also easily check that in this case, not all degree zero divisors principal, because obviously for two distinct places, its difference has degree 0, but as we have seen in the previous page, for distinct points, for distinct places, they cannot be equivalent to each other. And indeed, this observation also allows us to introduce the notion of degree 0 divisors. And indeed, it forms a subgroup of the divisor group, and it contains the principal divisors of the function field, because we know that every principal divisor has degree 0. And this subgroup structure allows us to consider the factor group or the quotient group. In the literature, it is denoted by the Jacobian of F. And also called the Jacobian of F. And for the elliptic curves case, the beauty of this structure will be its one-to-one correspondence between the rational places or the rational points of the elliptic functions, of the elliptic function fields, set of all rational places. So that means we are able to consider a bijection between the rational places of F and this group structure Jacobian by mapping a place P to the equivalence class of its difference between the base point O. And actually the final claim will be this correspondence also will allow us to remove the group structure of the Jacobian to the rational place, and indeed, without using any elliptic curve arithmetic, we will be able to conclude that elliptic curves has also group structure.